For the attention, we already learned the simple calculation for the attention. Now let's look at this example. There is a sentence. Bob is very cute and he is a dog. By looking at this sentence, so there are some words which are relevant. What does it mean? We know the word Bob, it is starting with big letter P. Then maybe this is the dog's name. Okay. Bob is very cute and he is a dog. Okay, so from this one we know that okay, Bob might be related to dog name and is very cute. So the word he is to Bob, and the word he is also relevant to dog. The Bob is also relevant to dog. So when we know that, okay, I know Bob is dog because based on this sentence, there is a relationship between Bob and dog, and then he and dog, he and Bob. If you look at this one, the word he with the surrounding text, he and is, he and a, he and an, he and cute, it's not that relevant. It's not that high for the relevancy because we cannot see anything. But we know that there is a high relationship between this one. So we can put attention. We can do the attention on those important words or for those relevant words. For the attention block, we can see something like this one. After we have the word, we can see the key and the value. As you know before from the calculation, we have the key values and we want to check the query. So the query means the word that might be relevant to other words. So let's say if I have Bob, so I think this is one of the query because I want to know whether it has some relevant word. And I know that there is a relevant word which is he. And I want to know whether there is another relevant word. Okay, I know there is a relevant word which is dog. So the query, we can assign a word and we will check based on the key and based on the value. So after we have the queries, we will check with the key and there will be a mechanism. This is a mathematical formulation to combine these two. So here is the matrix multiplication. As I mentioned to you, we just use the simple multiplication. But if it is a form of matrix, then we can do the matrix multiplication. So that's why we call it the mat mul here. And after we do the matrix multiplication, usually there is a way to do the normalization. We need to normalize the value of the multiplication, and then the matrix that has been normalized, we again do the matrix multiplication after we normalize it to get the attention values. So these attention values, it means it is the embedding with the context. In more complicated things in the attention block, we will do the forward propagation and backward propagation. If you already know the neural network, we have the forward propagation. It means we will do the calculation and then we will check the error. So we will return back. And then again, we will do iteration until the weight is converged. When the weight is converged or the sigma or the delta weight is very small, then we stop. Or sometimes we want to determine how many epoch that we want to do, and we stop. So this is the attention block with single. But we can also do attention block with multi-head attention. It means there will be some words that we want to focus on. So for example, this word, as I mentioned to you, Bug is very cute and he is a dog. So the Bug, cute, and he should have some significance or relevance with the word dog. So it means not only one, but there might be several words and they are in the same importance, or we want to find whether they are significant or not. This word say that the dog's name is Buck, it is male dog, and that he is a cute dog. So it means those words have a high relevancy. And if it is high relevancy, it means just one attention mechanism may not be able to correctly identify these three words as relevant to dog. Thus, we can say that three attention are better to signify the three words with the word. So if we have more than one, it means we will have multi-head attention. In this case, because I want to focus on three words, I can create three weights, or I can create three attention head. So the number of attention, it depends on how you make the definition about the importance. And at the end, we will have the final attention after we do this one. So the key will be a multiple of linear layer. The query also will be a multiple of linear layer, and the values also will be a multiple of linear layers. And we will do the matrix multiplication. So that's why this will be a very complicated and very big matrix. And at the end, we will have the final attention, not only a single value, but it is a matrix. So some of the previous works, they already did how to calculate the attention score. The other works like Luong, Badanao. So they proposed the attention score in 2015. And some of their attention score calculation is still relevant. However, many people already use the work from FAST1 in 2017. So the scale top, the name of the attention score, is represented with this formula. So now the attention score can be calculated using this formula based on the research from FAST1. So we will take a look more how to deal with this one, because this is representing the query, the key, and the value. So I will explain about the basic transformer. When we are in the NLP, in the natural language processing, you learn a lot about the traditional machine learning models. So we learn the very basic one, which is based on the statistical models. You learn about the probabilistic model, and then with the traditional machine learning model, we learn maybe we can use the KNN, we can use the logistic regression at the time, okay, and so on. And last week we learned about the deep learning models, how we can leverage the RNN. And now people try to adopt the transformer model. And in the transformer model, it requires this GPU. So if you want to do with the transformer model, make sure that you have a good spec of your laptop to run the model. Or yeah, you can try to use the GPU from Google Colab because they provide some free until certain of amount of memory. So the transformer architecture is on the publication published by Vaswani in 2017 with the attention mechanism. You can see like this one. And this transformer architecture, you can look at the detail. This one is dedicated for the encoder. This one is dedicated for the decoder. So the idea is still using the encoder and decoder mechanism. Encoder and decoder mechanism. However, the inside of the encoder and the inside of the decoder, it's just more complex way to calculate the matrix. For example, when we use the transformer, we have the input and then we convert the input into some input embeddings and we do the positional encoding. So we will learn later about the positional encoding. And we use the multi-head attention. We learned about the multi-head attention before. And after we have the multi-head attention, we would like to add and normalize the value. After we add and normalize the value, we input them into the neural network, which is feed forward. And the result from the neural network, we will again add and normalize. So this is the step of the encoder. And after we have this encoder, as you may know, we will do the decoder. So the decoder step is this one. So the decoder step, we will use the multi-head attention again, but it is must. Must means we will keep some words without a proper information. And we have the result, and the result will be used for the multi-head attention and the feed forward neural network. At the end, we would like to use the linear activation and do the softmax before we calculate the output properly. So last week we already done some of the activation. We can use like we can use like sigmoid. In the architecture of transformer, we use linear. And we can use the softmax function. We learn about the softmax using the E function. E divided by the sigma. So in detail, we can see the architecture like this one. So this is the encoding steps. So this is the encoding step. And then after we do the encoding step, we have the attention mechanism. The attention mechanism requires the query, keys, and value. Okay, so we learned before we have the Q, this is the query, multiplied by K. So we have the QK similarity. After we have the QK similarity, we want to map it into the values. So this one will be multiplied with the value after we do the softmax. Okay. And the relevant info will enter this decoder. So if you can see the diagram, it can be something like this one. So the input, it will be multiplied with the width of Q, with the width of K, and at the end, we will multiply with the V. So the combination of Q, K, and V, it will be the attention mechanism. So the attention mechanism, the attention value will be based on the softmax, and this is the formula. So this is the formula that has been proposed by Paswani in 2017. So if you can see, this is the softmax of Q multiplied by K transpose divided by the number of dk multiplied by V. So the idea is still the same. This one QK similarity. Okay. And we will do the normalization. After we do the normalization, we will multiply with the P. We will multiply with P. So the normalization here, last in the example that I showed you before, I used the softmax. So with the softmax, we can get the weight with the normalization. So this shows an example. Let's say I have an input. It is in the French. It is in the French language. And I want to use the transformer to show the output. I am a student, for example. So the input, it will go to the encoder, and the encoder can be in many layers, not only one, but it can be many layers. After it goes to many layers, so this encoder can be embedded to every of the decoder, and this decoder will show the output. So there are many variations how to use the attention. In the encoder, you can set the attention before the forward. For the decoder, you can do the self attention before the encoder decoder attention, and before we go to the feed forward. So that's what I mentioned before. In the previous one, I simplified the example with the Q of Alice with only one length. But actually, when we do with the neural network, we need to do like the embedding. After we have an embedding, we will need a query, which is a matrix. And then we will multiply with K, which is a matrix. And we will multiply with 3. This is also another matrix. The same with another word, let's say is, we will create the embedding, we have another query, we have k, and we have value, and then we need to calculate this one. So we will create a weight of q, weight of k, and weight of v. So what we already look at the formula, it is just a flow to show that once we have the each word, okay, and then we do the multiplication, and we got the weight, and we get the q0, k0, v0, and then we have the z0. So we can go to check with another input. We can go to check another input, and then we will have the concatenation of all the weight, and we will have the final score. So this is just one flow, but we will do this repetition for example, 100 people, or for, let's say, if you have the learning rate, or if you have the convergence stopping criteria, then it will stop based on that criteria. So the transformer, the basic transformer, it uses the scale dot product attention, and also they already applied the multi-head attention, and there is a position-wise feed-forward networks, and embedding and softmax, and the most important part is the positional encoding. So they want to know whether the placement of one word, it will be relevant to another word. So the scale product, so this is the formula by the Paswani. So we already looked at the formula. We multiply the Q and the K, and then we do the softmax. So we do the normalization, and then at the end we multiply with V. For the multi-head, okay, because we have several attention, then we just do the concatenation. The concatenation means we just combine. If we have the first attention, we have the second attention, we have the third attention, then we will just combine all of them into one attention. The position wise means I would like to see the position, and each of the position will be entered into the feed forward network. So we will check later what is the positional encoding. And for the embedding and softmax, the embedding widths, we will multiply the hidden layer every round, and then we will do the softmax linear transformation. So there's an article about how to do the share embedding widths and the softmax linear transformation in this paper. And the positional encoding, is required when we have the input. So after we have the input embedding, it is necessary to do the positional encoding. It is to check the sequence position. The reason of this positional encoding, there is no RNN to model the sequence position. So if you still remember, like Bob is cute and he is a dog. So we do not know where is the position of he, where is the position of dog? In our eye, it is easy that, okay, he is in the position 1, 2, 3, 4, 5. But in the computer, yeah, it is not easy that we can look at the relationship between bug and he. It is not easy to see the relationship between bug and dog. So there are some works that focus on the positional embedding. In the positional embeddings, they use the sinusoid function. Sinusoid function means we use the sine, sinus and cosinus. So this is the formula, and you can take a look on this paper. So let's just look at the very easy way to deal with the positional encoding. So the positional encoding is a technique. It is used in models like transformer to provide positional information to the model by adding position dependent signals to word embedding. And it allows the model to incorporate the order of words in the input sequence. So let me just give you with very simple example, like I am a robot. So I took this one from one article. I have word. I am a robot. If you learn from the last week code, we have the index. What is index? We learn if you want to put into a neural network, every word should have index. So we say that in the index 0, let's make it as the word I. For index 1, okay, let's make it as the word M. For index 2, let's put it as the word A. And for index 3, let's put it as the word robot. Okay. And this is index of token. And we can create the positional encoding matrix. So the positional encoding matrix, we can use the sinus and cosinus. Sinus and cosinus. So in this sinus and cosinus, yeah, we will do the repetition. For example, now in the I, or in the repetition for the position P00. So in the position P00, I will use the sinus 0. Sinus 0 is 0. The position 1, 0. The position 1, 0, it means that I will check this index, which is 1, and divide it by, because this is still in the position I equals to 0. So it is in the position 1. Or in this case, sinus 0 is 0 divided by 1. This is 1 divided by 1. This is index 2 in the first iteration. This is index 3 in the first iteration. Then we have I equals to 0 for the positional encoding at the first matrix. For the next I, which is 0, we want to calculate using the cosinus. The position now becomes P01, P01, and then P11, and then P21, and then P31. And we want to apply the cosinus function. The same with this one, because we are in the location of 1. So 0 divided by 1 with the cosinus 0 divided by 1, it means cosinus 0 is 1. And then we have cosinus 1 divided by 1, we have cosinus 2 divided by 1, and then we have cosinus 3 divided by 1. And yeah, we can get this value. This is for I equals to 0. Then we go to the I equals to 1. So I equals to 1 means I will do the next step by looking at this one. 10,000 power of 2 divided by I divided by the model. So in this case, now if you, let's say we have the n is 100, then we have the sinus 0, so 0 divided by 10. Okay, so you can calculate later with the n and this one, where 10,000 2 multiplied by the I divided by the t model. So we have 0 divided by 10. 0 means the index, and 10 is the division based on the d model and the n. And this one, we have the index 1 divided by 10. This one, index 2 divided by 10. This one, index 3 divided by 10. And we get this value for the position P02. And we can get also for the position 03 and so on. So we can calculate until we have a certain matrix. Let's say if it is d equals to 4, then we have only 4. So it depends how you can define the d and also the n. I give you one code to give more understanding how the positional encoding works. So this is the code for getting the positional encoding. So the positional encoding, it will be based on the sequence length, and then D, and then N, which is, you can define the N. At first, we will create the 0 for all position will be 0, and then we will do the repetition until we have a part until the length. So here we will do until the length, and then because D is 4, so we will divide with 2. We will divide with 2. Why? Because when we have 4, there will be 2 positions. The first will be with the sine, the second will be with cos, sinus, and then the other, it will be based on the sinus and it will be based on the cosinus. And we can do like this one, the denominator, it is the power of n comma 2 multiplied by I divided by d. So this is based on the paper that I mentioned to you. Yeah, this is the function. This is the function that has been applied by the paper here, and it has been used for the positional encoding in the transformer network. So we can use this denominator, and then we calculate the positional encoding k comma 2 multiplied by I and pk2 multiplied by I plus 1. The first is using the sinus, and the second is using the cosinus. So after we calculate this one, then we can get this is the positional encoding, where the data has a sequence length is equals to 4 and d equals to 4 and n equals 1. So using this idea, we can do the plotting. So the plotting means whenever we have the data, we want to know how many data that we can generate and how about the shape of the data in the sinus and the cosinus. So with the plot sinusoid, so we want to check this on the k and then d and then the n. So this is this on the paper. We can generate the k equals to 0, k equals to 4 like this one, k equals to 8 like this one, k equals to 12 like this one. So the basic idea of this positional encoding, we want to show the diversity of the text. So they do some experiment. They do some experiment with many n, and they can say that n equals to 10,000 is the best according to their experiment. That's why with their experiment, they use the 10,000 to deal with the positional encoding, and you can see here the division using the 10,000 using the 10,000. So the final output of the positional encoding layer, as you know, we have the word as the input. I am a robot. The word embedding means you can put any word embedding such as word to fact, or you can use the glove, you can use fast text, and etc. After you have a matrix from this word embedding, you can do the positional encoding matrix. So we will check what is the position from the sinus and the cosinus function, and we will have a matrix to indicate the positional of that particular word. So I can know the positional encoding of the word I, the positional encoding of the word M, and the positional encoding of the word and the positional encoding of the word. And after we have this one, then we can do next for the multi-head attention. We can do with the next for the feed-forward network as the encoder, and we can do with the decoder. So this is the paper that you can refer to for attention. So if you want to understand more about the attention, you can refer to this paper. And the paper mentioned some kind of experiment results. So I just took the experiment results from the paper. They claim that when they use the self-attention, the complexity per layer is this one, with the sequential operation is O1, and the maximum path length is O1. So if you join the data structure and algorithm, we learn about this one. O n. It is the linear function. O n power 2. It is the quadratic function. Linear function is better than the quadratic function. But if you look at this one, the n power of 2 multiplied by d. Meanwhile, with the recurrent, it is n multiplied d power of 2. So the quadratic is different in the variable. So n is the sequence length and d is the representation dimension. So if the representation dimension is small, of course recurrent is better. But if the sequence length is small, then maybe self-attention is good. So it depends how you can address with n and d. If you use the convolutional, there might be another variable which is k. K is the kernel size of convolution. And if you have the self-attention restricted, restricted means the size of neighborhood in the restricted self-attention or in some of the neighborhood. Maybe if it is D is okay. So it is restricted only the neighborhood V and is, E and L. So you cannot do many relationship with the long sentence. Okay, so self-attention has O1 maximum path length. Then yeah, it means is very good. That's why people use self-attention in many blocks for this attention. This is another result. I think you can just take a look for the experiment. Maybe this can be one of the result in your project. So in your project, you need to calculate the PLEU if you can, and you can show the effectiveness of your result using the PLEU. In this case, this is the PLEU from English to Dutch, from English to French, and so on. Okay, next, I think I will explain on Tuesday about the Google Colab for report analysis. Any questions, comments?